Welcome to Dreaming Scientist's Sleepy Stories, a place where the mysteries of the universe guide you toward peaceful sleep. Faster-than-light travel is forbidden for anything moving through ordinary space. Every experiment ever performed confirms this limit with unyielding precision. Yet Einstein's general theory of relativity leaves a subtle opening. Space itself is not fixed. It can stretch, compress, and carry distances along with it. That distinction changes everything. The cosmic speed limit governs motion within spacetime, but it does not govern spacetime itself. Light in a vacuum travels at 299,792 kilometers per second, anchoring every clock, radar signal, and navigation system we rely on. But tonight, warp drive is not treated as fantasy. It is explored as a logical consequence of geometry, constrained by photons, curvature, and energy itself. Along the way, familiar obstacles reappear. Negative energy, fragile causality, and the quiet persistence of physics, striving to reconcile what the equations allow with what nature permits. The most unsettling aspect of faster-than-light travel is not its seeming impossibility, but that mathematics describing the universe never entirely forbade it. In laboratories, no particle, ship, or signal has ever outrun light. Particle accelerators confirm it. Atomic clocks aboard satellites depend on it. Laser-ranging experiments spanning millions of kilometers agree with extraordinary accuracy. And yet, when Einstein completed general relativity in 1915, he redefined motion itself. Gravity was no longer a force pulling objects through space, it became the curvature of spacetime. Mass and energy determine how spacetime bends, and that curvature dictates how matter moves. A radical idea, now confirmed time and again. Gravitational waves detected in 2015 illustrate the distinction. They are not objects racing faster than light, they are distortions of spacetime itself, stretching and compressing distances as they pass Earth. No object breaks the speed limit. Space simply reshapes. Relativity restricts local motion, but places no universal cap on how quickly spacetime itself can evolve. The early universe provides a striking example. During cosmic inflation, regions of space expanded away from each other at an effective rate far exceeding light speed. Galaxies were not moving through space faster than light, the space between them was growing. Each region behaved normally within its own neighborhood. This is the doorway through which warp drive enters physics, not a loophole, but a direct implication of Einstein's equations. In 1994, Miguel Alcubierre explored this mathematically. Without new laws or exotic particles, he demonstrated that general relativity allows spacetime to contract in front of a region and expand behind it. A spacecraft could remain locally at rest inside this region, never exceeding the speed of light relative to its surroundings. From the outside, however, the distance between departure and destination would shrink dramatically. The ship would not outrun light, the geometry of the path would change. Alcubierre's solution described a warp bubble, carrying its contents along without subjecting them to extreme acceleration. Inside, clocks tick normally. Instruments function as expected. There is no relativistic mass increase, no crushing forces. It is not propulsion in the traditional sense. It is spacetime manipulation. Physicists noticed immediately that, on paper, the solution respected local causality. No signal inside the bubble exceeds light speed. Alcubierre emphasized that this spacetime could exist within general relativity without introducing new physics. That insight has shaped decades of discussion. History offers perspective. Gravitational waves were once dismissed as mathematical curiosities, predicted in 1916, but not observed for nearly a century. Warp drive now occupies a similar place, permitted by equations, unsupported by observation, constrained by conditions that may never be physically achievable. One constraint appears immediately. To bend spacetime this aggressively, the equations demand regions of negative energy, energy of the wrong sign. And from that requirement, the real challenges begin. Everyday experience shows energy as positive. Mass contributes energy. Radiation contributes energy. Even empty space is filled with quantum fields carrying measurable energy. Negative energy seems fictional, but physics does not forbid it entirely. Quantum theory allows narrow circumstances where energy dips below the surrounding vacuum. The Casimir effect is the clearest example. Two conductive plates placed extremely close together restrict quantum fluctuations between them, creating a tiny region of negative energy density. Measured repeatedly, the forces match predictions perfectly, but the scale is minuscule. The difference in scale is crucial. Known quantum effects produce tiny negative energy. To warp spacetime dramatically, Alcubierre's calculations showed, would require energy comparable to the mass energy of entire stars. The mathematics permits warp drive, but nature does not cooperate. The equations remain precise and unbroken, but the universe, as far as evidence shows, is far more demanding. Even so, the subject did not end there. Over time, researchers revisited the assumptions embedded in the original model. Harold "Sonny" White, working with NASA's EagleWorks laboratory, explored alternative warp geometries that redistributed how spacetime was distorted. By changing the shape and thickness of the hypothetical warp region, the energy requirements could be reduced by many orders of magnitude. These revisions did not eliminate the need for negative energy, but they demonstrated something important. The original estimate was not unique. Geometry mattered. Distribution mattered. The challenge was not just the amount of energy, but how spacetime was being asked to curve. Astrophysical observations reinforce the caution suggested by these results. Near black holes, spacetime curvature becomes extreme, yet it still obeys the same equations without ever forming warp-like configurations. Precision measurements of stellar orbits near the supermassive black hole at the center of the Milky Way confirm general relativity to remarkable accuracy. Observations of early galaxies reveal how structure emerged under gravity alone, without exotic distortions of spacetime. In every known case, nature uses curvature sparingly. It never approaches the engineered configurations a warp bubble would require. This contrast highlights a broader lesson. General relativity admits many mathematical solutions that appear physically implausible. Closed time-like curves, rotating universes, and traversable wormholes all emerge naturally from the equations, yet none have observational support. Warp drive may belong to this category, internally consistent within mathematics, but unrealized in nature. Carl Sagan often warned that extraordinary claims demand extraordinary evidence. Warp drive does not yet make a claim. It poses a question. Can spacetime be deliberately shaped, or are these solutions merely formal possibilities without physical pathways? Another limitation appears when causality is examined carefully. Even if a warp bubble avoids local violations of the speed of light, its global structure can introduce horizons. Information from inside the bubble may be unable to reach its front edge. Light attempting to propagate forward can pile up at boundaries. These effects are not speculative. They follow directly from how light rays behave in strongly curved spacetime. Photons trace the geometry faithfully, and in doing so they expose where a solution breaks down operationally. A spacetime that looks benign in equations can become unusable once signal propagation is considered. History again offers perspective. Nuclear fusion began as a theoretical consequence of quantum mechanics and stellar physics long before it became an experimental pursuit. Decades passed before controlled fusion approached practical relevance, and even now it remains incomplete. Warp drive sits far earlier on that timeline. The physics allows discussion. The evidence demands restraint. What ultimately makes warp drive compelling is not the promise of interstellar travel, but what it reveals about spacetime itself. General relativity does not describe a rigid backdrop. It describes a dynamic structure that stretches, compresses, and responds to energy. That flexibility explains gravitational lensing, time dilation measured by orbiting clocks, and the accelerating expansion of the universe without violating local speed limits. Warp drive forces that flexibility into sharp focus. If spacetime could expand faster than light during cosmic inflation, if gravitational waves can alter distances across Earth, and if curvature can redirect light near massive objects, then the deeper mystery is not why warp-like solutions exist, but why spacetime seems so resistant to being shaped intentionally. The answer may lie in energy conditions, quantum instabilities, or constraints not yet fully understood. Or it may reflect a simpler truth. Mathematics describes more possibilities than nature chooses to realize. Einstein himself cautioned against confusing equations with reality. As far as mathematics refers to reality, he noted, it is not certain. Warp drive lives precisely at that boundary, where logical consistency survives but physical realization fades. As that boundary becomes clearer, one thing stands out. When spacetime is stressed, not all probes are equal. Light remains the most reliable guide. Photons follow geometry without deviation, and when spacetime approaches its limits, their paths reveal where motion is truly allowed. With that in mind, the next step becomes unavoidable. Understanding why faster-than-light travel fails so decisively in ordinary space, long before warp geometry is even considered. That failure forced physics to reconsider its most basic assumptions. Einstein did not complicate the picture. He simplified it by removing ideas that were quietly taken for granted. Space and time were no longer treated as separate, absolute backgrounds. They merged into a single structure, spacetime. Distances and durations were no longer universal quantities. What mattered instead were spacetime intervals, quantities all observers could agree on. Once this shift occurred, the speed limit emerged naturally. Faster-than-light motion through ordinary space would shatter causality. Events could be reordered depending on the observer. A signal might be received before it was sent. Cause and effect would lose their universal meaning. This is not a philosophical worry. It falls straight out of the mathematics. If any object could exceed light speed in normal space, there would always exist a reference frame in which effects precede causes. Because relativity forbids preferred frames, there is no way to contain the damage. Causality must hold for everyone, or it holds for no one at all. Observations reinforce this conclusion. High-energy astrophysical events such as gamma-ray bursts emit photons spanning enormous energy ranges. If faster-than-light effects were available in ordinary space, higher-energy photons would arrive noticeably earlier or later after traveling across billions of light-years. They do not. Arrival times match relativistic predictions with remarkable precision. Even after crossing most of the observable universe, light behaves exactly as spacetime demands. Yet the story does not end there. The light barrier appears absolute only if motion through space is the only possibility. General relativity quietly introduces another option. Space itself can evolve. The expanding universe provides direct evidence. Distant galaxies recede faster the farther away they are. Beyond a certain distance, that recession speed exceeds the speed of light. No law is violated because galaxies are not sprinting through space. The space between them is stretching. Measurements of the cosmic microwave background confirm that this expansion has been ongoing for more than 13 billion years. The distinction is critical. Relativity restricts motion within spacetime, not the rate at which spacetime itself can change. This is how cosmic inflation operated in the early universe. Vast regions separated at effective speeds far exceeding light, yet no local signal ever outran it. Every region obeyed the speed limit in its own neighborhood. This subtlety is often misunderstood. Faster-than-light travel through ordinary space remains forbidden. Faster-than-light separation caused by spacetime evolution is permitted. These are fundamentally different phenomena. Carl Sagan emphasized this discipline repeatedly. Wonder, he argued, does not require abandoning rigor. The speed of light is not a guideline. It is the scaffold that holds causality together. This distinction matters deeply for warp drive ideas. Warp concepts do not propose outrunning light within space. They attempt to bypass ordinary space altogether. But before that move can make sense, the impossibility of faster-than-light motion must be understood clearly. Energy provides another angle. In classical mechanics, speed grows proportionally with energy. In relativity, the relationship curves sharply. As velocity increases, energy requirements climb faster and faster. Near the speed of light, the required energy diverges toward infinity. Particle accelerators demonstrate this daily. Protons pushed to near-light speeds demand enormous energy increases for ever smaller gains in velocity. The boundary never yields. Inertia behaves the same way. As objects approach light speed, resistance to acceleration increases dramatically. This is not because mass grows in a simple sense, but because spacetime itself reshapes how force and motion relate. Time also participates. Moving clocks slow down. This effect has been measured using unstable particles, aircraft-mounted atomic clocks, and satellites. As speed increases, proper time ticks more slowly. At light speed, it ceases entirely. These are not decorative features of theory. They are constraints. Together, they form a tightly interlocked structure that leaves no gaps for shortcuts through normal spacetime. Quantum mechanics does not loosen the rules. Entanglement produces correlations that appear instantaneous, but it cannot transmit usable information faster than light. This limitation has been verified repeatedly. Causality remains intact. Across all domains, the conclusion is the same. Faster-than-light travel through ordinary spacetime conflicts with energy conservation, causality, and the geometric structure of reality itself. Physicists do not treat the light limit as an inconvenience. They treat it as a clue. It tells us how the universe is built. And yet, general relativity remains indifferent to intuition. It describes what spacetime can do, not what technology can currently exploit. When solutions appear that reshape distances instead of racing across them, attention naturally shifts. Not because the limit is weak, but because it is precise. Normal spacetime enforces the light barrier relentlessly. Every experiment confirms it. Every satellite depends on it. The wall does not crack because it is not made of matter. It is woven into spacetime's structure. But once spacetime is treated as dynamic rather than fixed, the question subtly changes. The speed limit remains untouched, yet the geometry it governs need not stay frozen. Under those conditions, distance itself can change without anything ever exceeding the speed of light. Part 3. How warp drive avoids outrunning light. The most disruptive aspect of warp drive is not extreme speed. It is the absence of speed altogether. Inside a warp bubble, nothing moves fast. This single fact overturns nearly every intuition shaped by rockets and engines, and it explains why warp solutions appear in Einstein's equations without breaking relativity. In ordinary space, motion is defined by changing position over time. Speed is distance divided by duration, and light sets the ultimate conversion between the two. Warp drive does not challenge that relationship. It redefines distance. This only makes sense once spacetime is treated as physical. General relativity does not describe space as a rigid container. It describes a responsive structure shaped by energy and momentum. When gravitational waves passed through Earth in 2015, detected by LIGO, the planet did not move to meet them. Space itself stretched and compressed by tiny amounts. The detectors registered geometry changing around them. Warp drive begins from the same principle. Miguel Alcubierre asked a narrow but radical question. If spacetime can stretch and compress, could it be arranged asymmetrically? Could space contract ahead of a region and expand behind it? His solution did not involve thrust. It involved curvature. Inside the warped region, spacetime remained calm and nearly flat. Outside, geometry changed. From the viewpoint of the crew, nothing dramatic occurred. No acceleration. No time dilation. No relativistic stress. Locally, all laws of physics behaved normally. From far away, however, the picture changed. The region itself moved because spacetime around it evolved. Distances ahead shortened. Distances behind lengthened. The ship appeared to cross enormous separations faster than light could in unaltered space. Yet no photon was overtaken. No signal violated causality. This mirrors cosmic expansion. Galaxies beyond a certain distance recede faster than light, not because they move too fast, but because space between them grows. Measurements of cosmic expansion confirm this behavior with extraordinary accuracy. Warp drive applies the same logic locally. The ship does not ride faster than light. It remains inside a moving geometry. Light follows spacetime paths. Warp drive reshapes those paths. An analogy helps cautiously. Standing on a moving walkway, you are nearly motionless relative to the belt, yet you cross the terminal quickly. The walkway does the work by changing the reference frame. Warp drive proposes a spacetime version of this idea, with geometry replacing machinery. Astronomy reinforces why this is not automatically forbidden. Observations of early galaxies reveal vast separations established rapidly after the Big Bang. Those distances grew because spacetime expanded. Light behaved normally within it. Geometry changed around it. Einstein anticipated this flexibility but remained cautious. Not every mathematical solution corresponds to physical reality. Warp drive may represent a structure spacetime permits, but nature declines to build. That uncertainty is precisely what makes it worth examining, not as engineering fantasy, but as a probe into the limits of spacetime itself. Warp drive lives in a quiet, uncertain space within physics, not because it promises speed, but because it removes the idea of racing altogether. When motion is no longer a sprint through space, acceleration quietly fades away. Ordinary spacecraft must push hard, building speed through force. That force presses bodies into seats, strains materials, and taxes both machines and humans. Warp drive escapes this entirely. Inside the bubble, nothing is being pushed. You feel no pull, no shove, no resistance. The ship drifts as if it were resting in deep, empty space. This absence of acceleration is not a luxury. It is essential. In relativity, acceleration is deeply tied to inertia and energy. Remove acceleration, and many familiar penalties dissolve with it. Yet the calm comes at a cost. To bend spacetime itself, energy must be arranged with extraordinary precision. In the Alcubierre framework, regions surrounding the bubble must contain negative energy density. This requirement is not optional. It follows directly from Einstein's equations, from how curvature responds to energy and momentum. Negative energy is not a fantasy. Quantum physics allows it to appear briefly in controlled conditions. The Casimir effect demonstrates this in laboratories, where empty space behaves in unexpected ways at microscopic scales. But these effects are fleeting and tiny. Warp drive demands something far beyond that. Large, stable regions of negative energy held in exact configurations. Studies, including those conducted by NASA, make the gap unmistakably clear. No known mechanism can create or sustain such conditions. This is not an engineering delay. It is a question we do not yet know how to ask, let alone answer. Still, even if warp drive remains unreachable, its logic teaches something essential. It reveals why the speed of light is not merely fast, but foundational. Light does more than travel quickly. It defines how events connect across spacetime. Warp drive does not try to outrun that definition. It steps aside from it. Rather than moving through the structure light defines, it reshapes the structure itself. Carl Sagan often reminded us that the universe does not owe us comfort or familiarity. It only owes consistency. Warp drive does not defy that consistency. It tests its boundaries. And as those boundaries are explored, deeper consequences emerge. One of them involves horizons. Within a warp bubble, the front edge can become unreachable from the inside. Signals may fail to arrive. Light sent forward can pile up without escaping. A boundary forms, not unlike the horizons studied around black holes. This behavior is not speculative. It follows naturally from how light moves through curved spacetime. Photons obey geometry. When geometry bends sharply, their paths bend with it. Astronomy shows this gently on cosmic scales. Light arcs around galaxy clusters because spacetime curves there. Warp drive would compress that effect into a local, extreme form. The lesson is unavoidable. Avoiding faster-than-light motion does not remove relativistic consequences. It simply trades one set of constraints for another. History advises patience. Einstein's equations allow many strange solutions: wormholes, rotating universes, loops in time. None have revealed themselves in nature. Warp drive may belong to this same category, a window into what spacetime permits, not necessarily what the universe constructs. Yet dismissing it would miss the deeper insight. Warp drive clarifies what the light limit truly governs. It is not a ceiling on ambition. It is a rule protecting local cause and effect. By removing the race, warp drive exposes spacetime's architecture more clearly than any engine ever could. Distances may change. Objects may not cheat within their immediate neighborhoods. That balance preserves both cosmic evolution and logical order. As attention shifts from raw speed to geometry, the problem quietly rearranges itself. Engines fade in importance. Curvature takes center stage. Motion becomes something subtler than velocity. And this leads to an unsettling realization. In warp drive physics, the spacecraft is not what moves. That idea feels wrong at first. Every journey, involves an object crossing space. Rockets burn fuel. Ships gain velocity. Distance shrinks because something travels. Warp drive breaks this story completely. The ship does not cross space. Space rearranges itself around the ship. To understand why this matters, you return to how motion is defined in general relativity. There is no absolute background. Position and time are measured relative to spacetime itself, a structure shaped by energy and momentum. Objects follow paths called geodesics, the shortest routes through curved geometry. These paths define what motion even means. Space agencies already account for this. Signals sent to probes near Mars arrive slightly later than classical physics predicts because spacetime near the Sun is curved. This delay, measured decades ago, confirmed that geometry alters distance and time without anything unusual happening to the spacecraft. The probe moved normally. Space was simply not flat. Warp drive takes this idea to its extreme. Inside the bubble, spacetime is arranged to remain calm and nearly flat. You detect no acceleration. No internal forces arise. Your clocks tick as they should. From within, it feels indistinguishable from standing still in deep space. Outside the bubble, geometry tells a different story. Space contracts ahead. Space expands behind. The ship remains centered in a stable region while the surrounding spacetime shifts. The bubble moves because the distortion moves, not because the ship gains speed. This distinction matters deeply. Energy, momentum, and causality are local quantities. Inside the bubble, special relativity holds perfectly. Light behaves normally. Nothing outruns it. From far away, observers see something else entirely. The distance between departure and destination shrinks because the metric defining that distance changes. An effective speed may appear faster than light, but no local observer ever witnesses a violation. Cosmology uses this same language. When missions mapped the cosmic microwave background, they revealed a universe whose geometry evolves. Distant galaxies separate not by racing through space, but because space between them grows. Locally, those galaxies remain slow. Warp drive borrows this cosmic behavior and applies it deliberately. So what actually moves? The answer is quiet and strange. The metric moves. The mathematical fabric defining distance and duration evolves. Rulers laid ahead would shorten. Those behind would lengthen. Clocks in different regions would drift out of sync, even though each behaves normally where it rests. This is not hypothetical. Gravitational waves have already shown it. When detectors observed spacetime ripples from merging black holes, the mirrors did not travel through space. The space between them changed. Geometry moved. the mirrors stayed still. Warp drive replaces brief ripples with a sustained distortion. Spacetime is not a substance, yet it has consequences. Light follows it. Matter responds to it. Time depends on it. Experiments have shown that Earth's rotation slightly drags spacetime around it, altering gyroscope orientations by tiny but measurable amounts. Geometry shifts without behaving like a fluid or carrying mass in the usual sense. Warp drive depends entirely on this dynamism. Navigation becomes a question of shaping curvature, not applying thrust. Direction comes from where space contracts. Speed comes from how rapidly geometry evolves. And with that comes a final complication. Control is no longer simple. There is no braking in the familiar sense. To stop, spacetime must relax back into stillness. To turn, the distortion must be reshaped. Early theoretical work shows that this control may be far more difficult than it first appears. The journey, it seems, is not about moving faster. It is about learning how space itself chooses to move. The Alcubierre bubble is framed by invisible boundaries, where spacetime curves sharply. These edges behave like moving horizons. Light approaching them from certain directions may never cross. Signals from inside may fail to reach the front. This is not philosophical. It emerges from the precise mathematics of curved spacetime. Photons, honest messengers of geometry, reveal everything. If a photon cannot escape, neither can a command signal. Observations of black holes offer a familiar parallel. Near an event horizon, spacetime curvature traps light, preventing it from escaping. Warp bubbles exhibit similar horizon-like behavior, even without singularities. The geometry itself enforces causal separation. This leads to a subtle but profound shift in control. The ship inside is not what moves. The occupants are not the agents of motion. The geometry governs everything. To navigate, you must influence the shape of spacetime itself, a task unlike steering any vehicle ever built. Once initiated, the warp bubble follows its own rules. Adjusting it may require access to regions that are causally disconnected, unreachable from inside. Physics reminds us of an old lesson: initiating a process is different from controlling it. Nuclear chain reactions demonstrated this decades ago. The mathematics may allow a configuration, but stability and manipulation demand far more. NASA's cautious approach reflects this. Studies focus not on claiming faster-than-light travel, but on understanding geometry, energy conditions, and stability. A ship that sits still locally may feel calm, but the underlying challenge remains. Another consequence follows naturally. If spacetime moves while the ship does not, inertial effects vanish. There is no force pressing you against walls, no warning of acceleration. Instruments detect zero. The crew floats as if suspended in deep space. Only external observations reveal that progress is being made. Astronauts aboard the International Space Station experience something similar, on a smaller scale. Orbiting Earth at 7 kilometers per second, they float freely inside. Locally, they feel still. Globally, they circle the planet every 90 minutes. Warp drive magnifies this separation. Orbital motion still involves velocity through space. Warp motion replaces velocity with evolving geometry. Carl Sagan often emphasized perspective in science. How events appear depends on where you stand. Warp drive embodies this principle. Inside, nothing seems to happen. Outside, the bubble appears to glide across space. The effect is paradoxical, defying everyday intuition while remaining consistent with the deeper laws of spacetime. The cost of this elegant illusion is steep. Maintaining the bubble demands energy distributions unlike anything seen in nature. Negative energy densities appear unavoidable, and quantum effects provide only microscopic hints. Observations from JWST remind us how conservative nature usually is. Even in extreme cosmic environments, curvature remains tightly linked to mass and energy. Engineered distortions on macroscopic scales do not occur. Yet, the lesson of warp drive is precise. Motion is not always about objects moving. Sometimes, Motion is about the stage itself changing shape. To ask what moves, we must abandon flat space intuition. What moves is the geometry defining distance. What remains still is the ship within its protected region. What limits the process is not speed, but the ability to sculpt spacetime without losing causal control. When spacetime itself flows while matter rests, the challenge narrows. Geometry alone is insufficient. Light itself becomes the ultimate judge. Photons, the uncompromising messengers of reality, expose every hidden flaw. In physics, light is never mere illumination. It measures distance, synchronizes clocks, and reveals the structure of spacetime with absolute precision. Warp drive theory is most fragile when photons enter the picture. Inside ordinary space, light follows the straightest paths allowed by geometry. Near massive objects, its path curves. Gravitational lensing, captured by ISA, demonstrates this clearly. Light from distant galaxies bends around massive clusters, forming arcs and multiple images. The galaxies themselves remain motionless. The light obeys the changing geometry. A warp bubble, however, introduces far more extreme curvature. Inside, spacetime remains nearly flat. Outside, it distorts sharply. At the bubble's boundary, this transition is abrupt. Here, photons reveal the true cost of warp motion. Imagine a photon emitted toward the front edge. Locally, it travels at the usual speed of light. Nothing unusual happens. But as it approaches the boundary, spacetime ahead contracts. Distances shrink faster than the photon can traverse them. In the ship's local frame, the photon slows relative to the boundary, though it never slows locally. The result is stark. In a sufficiently strong warp bubble, forward-emitted light may never escape. It accumulates near the front, compressed into a thin region of intense energy, an artificial horizon, reminiscent of black holes but without a singularity. From outside, incoming light bends, traps, or shifts energy as it encounters the bubble. Expanding space behind may stretch photons, blue shifting them to extreme energies. Even the cosmic microwave background, a steady 2.7 Kelvin radiation measured by the Planck mission, could be intensified to dangerous levels under compression. This is no minor detail. Photons carry energy and momentum, and their accumulation can create severe radiation pressure. Inside a warp bubble, light may exert powerful forces that ordinary physics cannot ignore. The photon problem is not abstract. It is causal. If light cannot cross the bubble boundary, neither can information. Signals may fail to reach the front, outside signals may fail to enter. The warp bubble may become partially isolated, a horizon problem, arising from the fundamental behavior of null paths in curved spacetime. From relativistic jets around supermassive black holes to laboratory measurements, photons have consistently validated general relativity. Warp drive must confront the same scrutiny. Frequency shifts, redshifts, and blue shifts complicate the problem further. Light climbing out of expanding regions loses energy, light in contracted regions gains energy. Cosmic radiation may transform from benign to hazardous. Every calculation points to one truth. Inside a warp bubble, photons are both guides and limits. They reveal where geometry can move and where causal control may fail. Any warp drive must manage light itself, not just matter, or the illusion collapses. Motion is no longer about the ship. Motion is about the geometry that carries it. The ship rests in its sanctuary, while spacetime performs the dance. And light, ever vigilant, ensures the dance never breaks the rules. Inside a warp bubble, everything interacts with the distorted geometry in ways both subtle and unforgiving. The equations do not promise safety, they describe consequences. Observers within may feel perfectly calm, unaware of the energy trapped at the bubble's edges. Photons, compressed and confined by the warped geometry, could release all at once when the bubble relaxes. The energy stored in that release could be catastrophic. These insights come not from fiction, but from careful physics. Scientists trace photon paths using the same tools that predict gravitational lensing and horizon behavior near black holes. The lesson is consistent: light is not decoration. It is the ultimate diagnostic. Carl Sagan often emphasized that understanding comes not from trusting elegant ideas, but from asking what observations would show. In a warp bubble, photons are the observers. They report faithfully on the shape of spacetime. Even if the interior remains flat, clocks inside the bubble must remain synchronized with the outside world for navigation to function. Light signals are the only bridge between regions. If those signals cannot cross boundaries symmetrically, timekeeping fails. GPS satellites demonstrate this daily. Without continuous photon exchange, positioning collapses. Warp bubbles introduce regions where photon exchange is asymmetric or impossible, making the ship locally calm but globally blind. Photon behavior also constrains how a warp bubble can form or dissipate. Rapidly changing curvature can create particle production effects, akin to those seen near cosmological horizons. Quantum field theory predicts that shifting spacetime can materialize particles from vacuum fluctuations. These are subtle, yet real effects studied in early universe cosmology and black hole physics. Warp drive designs would need to account for them. Light does not forbid warp drive outright. It clarifies the cost. Photons reveal that avoiding faster-than-light motion does not avoid extreme relativistic consequences. It simply relocates them to regions where geometry bends sharply. The elegance of warp drive lies in its respect for local limits. Its fragility lies in the global behavior of light. Physicists summarize it simply: equations allow solutions, photons test them. Every observation of spacetime, from lensing to time dilation, reinforces this truth. Geometry is accountable to how light moves. Warp drive exists on that boundary of accountability, surviving only while photon behavior remains manageable. Once the discussion turns to sustaining the bubble, one requirement emerges with brutal clarity: exotic or negative energy. Ordinary matter cannot do the job. Every confirmed model that bends spacetime enough to mislead light demands energy arranged in ways nature has never provided. In general relativity, curvature responds directly to energy and momentum. Positive energy bends spacetime inward. Matter pulls geometry toward itself. But a warp bubble requires contraction in front and expansion behind. While contraction can be produced by positive energy, the expansion demands something more: energy density that is negative relative to the vacuum. This is not speculation. It comes directly from Einstein's equations applied to the Alcubierre geometry. Stress energy distributions required to sustain the bubble include terms no ordinary matter can supply. Physicists formalize this with energy conditions, mathematical statements about how energy behaves in realistic systems. For decades, these conditions matched every known form of matter. Warp drive breaks them. Quantum theory complicates the picture further. The vacuum is not zero. It fluctuates. Under certain conditions, these fluctuations dip below the average, producing negative energy. The Casimir effect demonstrates this. Two uncharged metal plates placed micrometers apart experience a tiny attractive force because vacuum modes inside the plates differ from those outside. The energy density between them is lower than the surrounding vacuum. Experiments confirm this with high precision, proving negative energy is not forbidden. Scale, however, is critical. The Casimir effect operates over microscopic distances. Warp drive requires macroscopic, stable, negative energy arranged precisely and maintained over time. NASA assessments emphasize the gap. Quantum effects allow fleeting violations of classical energy conditions, but they cannot be amplified arbitrarily without destabilizing the vacuum. Quantum inequalities strictly limit how much negative energy can exist, for how long, and over what volume. Warp drive models confront these limits directly. Physicists have explored whether clever geometries could reduce the required energy. Modified Alcubierre bubbles redistribute curvature, flatten gradients, and shrink extreme regions. Some calculations show dramatic reductions in total energy requirements. But none eliminate the need for negative energy entirely. This persistence is structural, not incidental. Nature provides no examples of stable macroscopic regions dominated by negative energy. Even in extreme astrophysical environments, neutron stars, black holes, or the early universe, energy densities remain positive in the classical sense. Cosmic inflation may seem like an exception. During inflation, spacetime expanded at extraordinary rates, driven by an unusual form of energy. Yet even here, energy density was positive. It was pressure that was negative, not energy itself. Inflation stretches space, but does not produce the precise curvature required for a warp bubble. To understand why ordinary matter fails, consider compression. As density rises, pressure rises, reinforcing curvature toward attraction. Warp drive demands regions where energy and pressure combine to produce controlled repulsion. No known state of matter achieves this reliably. Exotic states, neutron-degenerate matter, quark matter, or even dark energy, fall short. Dark energy drives cosmic acceleration, but it is uniform, not locally manipulable. Warp drive requires precise gradients. This is not a technological gap. It is conceptual. Warp drive asks spacetime to curve in ways that violate the expectations of both quantum field theory and classical gravity simultaneously. The elegance of the idea meets the stubbornness of reality. Some researchers have wondered whether negative mass could exist. In principle, negative mass would respond to forces in reverse, potentially producing the curvature a warp bubble requires. But the idea introduces immediate instabilities. Pairing negative and positive mass leads to runaway motion, violating conservation principles. No experimental evidence supports its existence. As Carl Sagan once warned, the universe is not obliged to conform to human ambition. Negative energy may appear within narrow quantum tolerances, but not as a tool to engineer geometry. Even if negative energy could be assembled, stability becomes a critical challenge. Quantum fluctuations tend to erase sharp energy gradients, equalizing densities. Maintaining a warp bubble would demand a continuous, precise supply of energy, counteracting natural relaxation. NASA's studies of quantum vacuum behavior emphasize this delicacy. The vacuum is not passive, it reacts violently when disturbed, producing particles, radiation, and instabilities. Hawking radiation near black holes emerges from the same principles. Rapid changes in spacetime generate real particles. Warp drive would impose far more extreme gradients across larger regions. Photons trapped at the bubble's boundaries, as discussed before, would interact with negative energy fields, producing feedback loops that current theory cannot stabilize. The conclusion grows inescapable. Warp drive is constrained not by one principle, but by an entire network of them. Negative energy exists, but only fleetingly. Spacetime can bend dramatically, but only when energy behaves within strict limits. Light can be guided by geometry, but excessive distortion punishes with horizons and instabilities. Warp drive asks the universe to approach every limit at once. This does not render the concept meaningless. It makes it diagnostic. By examining why exotic energy is required, physicists learn which features of spacetime are flexible and which are rigid. NASA's cautious language reflects this. Warp drive research is not about promising faster-than-light travel. It is about probing the deep relationship between geometry, energy, and quantum structure. Every attempt to remove negative energy from the equations has failed, revealing that spacetime resists being reshaped to preserve local calm while imposing global distortion. Once exotic energy enters the picture, the challenge shifts. It is no longer about producing energy, but understanding how its presence interacts with the structure of physical law itself. Energy conditions, stability, and the preservation of cause and effect all come under pressure. The most uncomfortable question in warp drive physics is not how fast it could go, but whether it could exist at all without quietly tearing apart the rules that keep the universe consistent. Every modern warp proposal begins by promising to respect energy laws, and almost all end up circling the same difficulty. Escape routes look convincing on paper, but collapse under closer inspection. Conservation of energy is not optional. It is among the most thoroughly tested principles in physics. Every gravity assist, every particle collision at CERN, every interplanetary fuel calculation confirms it. Energy does not disappear or appear from nowhere. It changes form, always accounted for. General relativity complicates global definitions, but local conservation remains intact. Warp drive challenges this predictability indirectly. The Alcubierre solution does not demand infinite energy or perpetual motion, but it violates the conditions under which energy behaves in familiar ways. These energy conditions, assumptions about how energy density and pressure relate in physically reasonable systems, underpin many theorems in relativity, preventing time paradoxes and unstable geometries. Warp drive breaks several of them. Researchers have tried to salvage the concept. Smoothing warp bubble gradients or redistributing curvature can reduce total energy dramatically. Dynamic bubbles that form, propagate, and dissipate attempt to relax quantum constraints. Even reinterpreting negative energy relative to different observers has been explored. None of these solutions eliminate violations entirely. Photons remain the ultimate witnesses, revealing whether energy flow respects causality. Observations of high-energy astrophysical jets show that even in extreme conditions, energy flows remain causal. Nature does not sustain the violations a warp bubble demands. Semi-classical gravity, where quantum fields interact with classical spacetime, was another avenue. Perhaps quantum effects could stabilize the geometry. But semi-classical analyses produce instabilities. Strong curvature interacts with quantum fields, generating particle creation. Energy extracted from the vacuum reappears as radiation. Instead of sustaining a warp bubble, the system radiates itself apart. These effects are real, studied in black hole evaporation and early universe cosmology. Rapidly changing geometry redistributes energy, it does not grant free resources. The deeper concern emerges when causality is considered alongside energy. Energy conditions are not arbitrary, they safeguard the sequence of cause and effect. Violating them can allow closed loops of influence, where events affect their own past. Warp drive skirts this edge. Locally, nothing exceeds light speed. But globally, effective faster-than-light paths can, under some conditions, create causal paradoxes. Physicists have demonstrated this mathematically. Faster-than-light effective travel allows closed time-like curves, where an event can influence itself. Einstein himself worried about such solutions, and later work reinforced caution. Stephen Hawking proposed the chronology protection conjecture, arguing that physics may prevent macroscopic violations of causality. Warp drive geometries bring this question to the forefront. If a bubble connects distant regions faster than light would through normal space, observers in different frames may disagree on the order of events. In some frames, arrival could precede departure. This is not a linguistic trick. It is a direct consequence of Lorentz transformations applied to superluminal effective spacetime. Energy conditions matter because they prevent these causal loops. Violating them opens doors mathematics alone cannot close. Warp drive is fascinating, but it sits at the boundary where energy, causality, and the structure of spacetime converge, and the universe guards that boundary jealously. Even the most precise navigation systems on NASA spacecraft depend on the universe obeying a simple rule: cause must precede effect. Every algorithm assumes events unfold in a predictable sequence. A single ambiguity could render guidance useless. While general relativity allows spacetime to bend and twist, every observation, from JWST to ISSA, shows that nature avoids situations where cause and effect could loop back on themselves. Black holes warp space intensely, yet their horizons safeguard the order of events rather than scramble it. Warp drives sit in a far more delicate zone. Instead of arising from mass, their horizons are born from engineered geometry. These boundaries can isolate regions of spacetime, bending the paths of signals so asymmetrically that influence may travel in one direction but not the other. If an observer can affect a region without being affected in return, the universe's bookkeeping of cause and effect falters. Physicists examining warp geometries found that avoiding paradoxes demands severe restrictions. In practice, these restrictions often make the bubble uncontrollable or impractical for a journey that returns to its starting point. Escape, it seems, is always on the edge of illusion. Looking back, rotating universe solutions discovered in the 1950s allowed closed loops in time everywhere, but none of them exist in reality. Observations of the cosmic microwave background, measured with pinpoint precision by Planck, confirm that nature favors geometries preserving global order. Carl Sagan often emphasized that the grandest ideas must survive contact with reality. For warp drive, reality's contact point is causality, and it pushes back. Even if a single warp trip could avoid paradox, multiple trips would compound the danger. Two bubbles moving relative to one another could form causal loops, even if each is individually stable. Quantum theory adds a further complication. Quantum fields, sensitive to causal structure, become unstable near such loops. Vacuum fluctuations escalate, energy densities spike, and spacetime can tear itself apart. These outcomes echo Hawking's chronology protection conjecture. The universe enforces temporal order, sometimes violently. Studies in semi-classical gravity confirm this feedback. Geometry shapes quantum fields, which in turn reshape geometry. Attempts to violate causality trigger runaway effects that erase the offending configuration. This is not judgment. It is a dynamical response. The warp drive dilemma is clear. Preserve causality, and the geometry becomes tightly restricted, likely unusable. Ignore causality, and instabilities destroy the bubble. Every effort to sidestep foundational rules encounters multiple barriers. This does not diminish the inquiry, it sharpens it. By confronting warp drive against causality, physicists gain insight into why time flows as it does. The arrow of time is encoded in spacetime itself. JWST's observations of early galaxies show the same order. Structures form, evolve, and age predictably. Light from distant epochs arrives in sequence. The universe remembers its past. Warp drive threatens to blur that memory. Even Einstein, who called the separation of past, present, and future a stubbornly persistent illusion, recognized that the sequence of events within the spacetime block remains consistent. Warp drive risks shuffling that sequence. Energy may be manipulated, geometry shaped, but if events lose their order, the process cannot be physically stable. NASA and ESA view this not as a prohibition but as a rule revealed by observation. Over 13.8 billion years, no causal violations have been detected. Any proposal that predicts them must explain why they do not already occur. A burden warp drive has yet to meet. If causality cannot be bent without consequence, even a perfectly constructed warp bubble faces limits beyond design. Interaction becomes the next problem. Detecting, controlling, and entering such a bubble is fraught with challenges dictated by horizons and the flow of information across them. The fundamental issue is this. Without light crossing the bubble boundary, there is no information, and without information, control is impossible. Every experiment, every spacecraft, every map of the stars depends on photons. NASA's Deep Space Network tracks spacecraft across billions of kilometers using radio photons. Gaia charts the positions of stars by counting and timing incoming light. If photons cannot pass, nothing can substitute. Warp drive theory predicts precisely these restrictions. In Alcubierre geometry, extreme curvature forms horizons that trap or redirect photons. Light emitted inside the bubble toward the front may never escape. From outside, photons can be bent, compressed, or frozen, reminiscent of the behavior near black hole horizons. ESA observations confirm that spacetime can immobilize light in such extreme conditions. Warp bubbles replicate these effects without singularities. This has immediate consequences. If photons cannot traverse the boundary symmetrically, neither can navigation signals or control commands. The bubble becomes isolated, presenting three key challenges. Control. Adjusting trajectory, speed, or orientation depends on signals reaching the edges. Inside a warp bubble, the geometry dictating motion may be unreachable. Steering from within may be impossible. Observation. Navigation relies on incoming light. If starlight is distorted, redshifted, or deflected unpredictably, familiar reference frames dissolve. The ship becomes blind. Entry and exit. Approaching or leaving a warp bubble subjects matter to extreme tidal gradients in spacetime, stretching and compressing it in ways unrelated to acceleration. Smooth traversal requires precise matching of geometry, a near impossible feat. observation extends beyond navigation. Warp bubbles could be detected from afar through lensing effects, bending and multiplying background stars, and releasing bursts of trapped photons. These signatures announce the bubble itself, not propulsion but the shifting of spacetime. Detection creates further vulnerability. Incoming cosmic radiation and interstellar particles interact unpredictably with the distorted geometry. Even cosmic microwave background photons could be dramatically blue-shifted at the front, accumulating energy that complicates control. Synchronization adds another layer. Spacecraft systems rely on coordinated clocks. GPS works because relativistic time dilation is precisely corrected. Inside a warp bubble, internal clocks may remain in sync locally, but external synchronization could fail entirely. Events inside and outside lose consistent ordering, eroding coordination with the outside universe. Carl Sagan emphasized that exploration without communication is indistinguishable from isolation. Warp drive risks becoming the ultimate isolation technology. Some suggest external control, shaping the bubble ahead of the ship. But horizons remain, and losing control leaves occupants helpless. The bubble evolves according to its own dynamics. History offers a warning. Early nuclear reactors showed that self-sustaining processes require failsafes. Warp drive, governed by spacetime itself, provides none. Observation from within is equally fraught. If light cannot leave, occupants cannot communicate. If light cannot enter, they cannot receive updates. Inside a warp bubble, the spacecraft becomes a closed system in a universe built on open exchange. NASA's long-duration missions depend on redundancy, continuous communication, and constant monitoring. Warp drive undermines all three. But this does not make it meaningless, it simply clarifies its nature. Warp drive is not a faster engine. It is a configuration of spacetime itself, with horizons that behave more like black holes than vehicles. Physicists take this seriously. Black hole horizons limit observation, control, and communication, and warp horizons impose similar restrictions, without requiring a collapsing mass. The universe has already taught us how such systems behave. They isolate, trap information, and resist manipulation. This resistance may be nature's way of enforcing consistency. Any system that could be freely controlled while bending spacetime at will would risk destabilizing causal order. NASA and ESA do not see this as a failure of imagination, but as a lesson written into spacetime itself. A warp drive, if it exists, would be less a ship you pilot and more a phenomenon you enter at great risk, with limited agency once inside. When all known constraints are taken seriously, the question sharpens. Can a warp drive exist as a stable physical system, or is it only a mathematical curiosity? Part 10. Is warp drive a real possibility, or a loophole of equations? For decades, general relativity has permitted warp-like solutions without contradiction. Yet, every observation of the cosmos remains silent on their existence. Physics has faced this moment before. Elegant mathematics has often raced ahead of empirical reality, only to be corrected by observation. Einstein's equations predicted gravitational waves in 1916, long before detectors could measure them. For almost a century, they were curiosities, until 2015, when observatories finally heard them pass through Earth. In that case, nature eventually agreed. Warp drive sits at a similar crossroads, but the comparison cuts both ways. For every mathematical prediction later confirmed, countless others remain unrealized. General relativity allows many exotic geometries. Closed time-like curves appear in rotating universe solutions. Traversable wormholes emerge under special energy conditions. Entire universes can be written on paper that spin, collapse, or loop through time. None have been observed. JWST, ESA, and NASA surveys reveal a universe that is surprisingly conservative at large scales. Warp drive belongs to this category, permitted mathematically, but unseen in reality. This distinction matters. Physics does not declare something real merely because equations allow it. Equations describe what is consistent within a theory. Nature selects which consistencies manifest. Across this series, A pattern has emerged. Warp drive respects local speed limits but strains global causality. It avoids traditional acceleration but demands extreme spacetime curvature. It satisfies Einstein's equations but challenges the energy conditions that keep those equations grounded. It can be written clearly on paper, yet resists control, observation, and stability. Each obstacle alone might be addressed, but together they form a coherent resistance. NASA and ESA do not dismiss warp drive as fantasy. They use it as a diagnostic tool, probing the limits of spacetime itself. The question shifts from transportation to structure. One lesson stands out: spacetime is flexible, but not freely malleable. It stretches under cosmic expansion, ripples from mergers, bends around mass and energy. Yet it resists deliberate reshaping that maintains local calm while imposing global distortion. Observations reinforce this. JWST sees early galaxies forming faster than expected, yet within gravitational rules. Gravitational waves ripple spacetime only briefly. Black holes warp geometry intensely, but at the cost of horizons and isolation. Every extreme phenomenon carries a price that preserves consistency. Warp drive tries to collect benefits without paying the cost. Energy conservation offers another anchor. Laws of physics have survived every experimental test. They adapt to relativity and quantum theory, but they do not vanish. Warp drive's reliance on exotic energy strains these principles. Quantum field theory allows brief, local violations, but forbids accumulation or control. Nature tolerates exceptions only when they cannot be exploited. Causality sharpens the boundary further. The order of events has remained intact across billions of years. Light from the early universe arrives on schedule. Stars evolve in predictable sequences. Even quantum signaling respects limits. Warp drive presses against this order, without offering a stable resolution. Hawking's intuition about chronology protection gains weight. The universe behaves as if it actively prevents configurations that would undermine temporal order. Warp drive flirts with that edge. Does this mean warp drive is impossible? Physics rarely answers in absolutes. Within our current understanding, warp drive exists where mathematics outpaces evidence. This does not invalidate the equations, it challenges our assumptions about their applicability. Carl Sagan often reminded us that science progresses by balancing openness with restraint. It is far better to understand the universe as it truly is than to persist in comforting delusion. Warp drive tests that balance. If new physics exists beyond general relativity and quantum field theory, perhaps warp drive could find a footing there. A deeper understanding of spacetime might allow controlled adjustments of energy conditions or causal structure. History allows this possibility. But until new phenomena are observed, warp drive remains a mathematical solution, lacking empirical support, and burdened by compounding constraints. That conclusion is not failure. It is achievement. It teaches that the universe cannot be tricked by clever geometry. Light, energy, causality, and quantum behavior all guard its structure. Warp drive has shown where spacetime bends, where it resists, and where our theories leave questions unanswered. Its lasting gift is insight, not transportation. As this journey through equations, observations, and limits comes to rest, hold this simple truth: the universe is vast, subtle, and consistent. Its rules are not barriers, but reflections of how deeply connected space, time, and matter truly are. Thank you for exploring these ideas together. May the rest of your night be calm and steady, as the universe continues its patient work around us, carrying you gently toward rest and sleep.